And we started with the basic unit, which is the self-information. And the self-information, that's from a random variable. So let's just assume you have your random variable x, which is in the alphabet x. Okay, so we can assume x is made up of components like x1, x2, blah 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 up to xn. Okay, so the self-information we say is given by, so self-information ixi is given by 1 over, log of 1 over pi. So we are assuming here that actually xi is distributed according to pi. So the distribution of x is pi. So the information of the self-information of x is 1 over log pi, which you can also write as negative just log pi. In this log to base 2, it gives you the information in bits. So the units here is bits. Then we said you can also find the average information. The average information content, and this is what we call uncertainty. So the uncertainty of this thing, so the average information content, h of x, which is also called the entropy, is given by the expectation of the self-information of, so that should be xi, okay? And this one, of course, will give us the expectation of this term log of 1 over pi, okay? So the expectation of that term log of 1 over pi is just going to be, this is going to be, so expectation, just take the summation, because we are talking about discrete random variables. So this from I is equals to 1 up to n, we have n of these random variables, then pi log to base 2 of 1 over pi. So that gives you the entropy, and the entropy is information bits per symbol. So the unit here is bits per symbol. So sometimes we write entropy like this as expectation, or in this format, or sometimes you can just write it as negative I from 1 to n pi log to base 2 of pi. Okay, so that would be the entropy, and the unit is in bits per symbol if the logarithm is to base 2. Now sometimes you have logarithm, so if the log is to base 2, that is in bits. If the log is to base e, your unit is going to be in nuts. Then instead, of course, we can assume, so this quantity here is called entropy. This quantity here is called entropy. Okay? That quantity there is called entropy. So you need to take note of that. And it's a measure, the average surprise or average uncertainty of the outcome. And in this case now, if you get an example, so now if you have a binary source, the binary source, that means its alphabet is made up of 2 components. So it can be 0 or 1. Its alphabet can be 0 or 1, which means the probability that x is equals to 0 is equals to p. Let me just start with x is equals to 1. And then the probability that x is equals to 0 is therefore going to be 1 minus p. Because all these probabilities should add up to 1. So if I take probabilities from I is equals to 1 to n of pi, this should give me 1. So I have a binary source, Then for binary source, if you calculate its entropy, it's going to give you a measure of H2 of P. But then sometimes this entropy can be represented as H of Pi of X. Because it's not a function of X. When we write it like that, it might look like a function of X, but this is a deterministic function, so it's a constant. Now, the binary entropy, if you calculate it, you're going to get it as P log to base 2 of 1 over P plus 1 minus P log to base 2, 1 over 1 minus P. Or you can actually just write it as P log to base 2, that's minus 1 minus P log to base 2 of 1 minus P. So for a coin flip or a Bernoulli random variable, then you can just get the entropy of a binary source. And this function here is called a binary entropy function. So it measures the quantity of information in these random variables. Then we looked at the plot of this entropy, and we saw for the binary entropy function, if you plot it, you're just going to have the minimum at 0 and 1. Okay, so actually these terms are undefined, and then the maximum is going to be when P is equals to a half. So this is the plot, and it's a concave function. So that's a concave function of the entropy. Now, what happens when X is uniform? When P of X is uniform. So, if you have a uniform distribution, so let's say X is distributed uniformly as, so M is the number of alphabets within our system. Number of the size of the alphabet. Now, if X is distributed uniformly as from 0 to M, that means that for each X, P of X is just going to be 1 over M. P of X is going to be 1 over M. So these are what you're calling P of I. Now I can do my entropy, which is going to be H of X is just equals to the sum from I is equals to 1 up to M. This is actually 1. No, 0. Up to M, then Pi log to base 2 1 over Pi. Okay? Log to base 2 1 over Pi. I'll do here M minus 1. So that it's 0 to M minus 1, which is 1 to M. So I can do this as, so I can also do the same thing here, but it's no problem. So I can do this thing as Pi is 1 over M. Log to base 2 1 over Pi is 1 over M, which is just equals to, now the summation we are adding from I is equals to M, so this is just a constant times M. So if you work this one out, you're going to get it as log to base 2 of M bits per symbol. So that's your entropy of this function. That's your entropy of this function. We're done that. Oh. So one thing about this, and I'm coming to this entropy maximization, so maybe before that you can work out. See that? source of the alphabet. You need to solve this question in like 1 minute. Okay, are you done? So you have a source with alphabet size 4, so S, which is made up of S0, S1 up to S3. Then we have with probabilities P0 of 0.5, P1 0.25, then P2 is equals to P3 of 0.125. Now, what is the entropy of this function? So what do we do, someone? William? Just tell me what to write. Yeah?
Get the probability.
We have it. So straight to the point, we are calculating entropy. So entropy H of S of this source is just going to be what? It's just going to be from I is equals to 0 up to 3 of Pi log of 2 Pi. So I can put my negative outside here, okay? So that I don't do 1 over Pi. So that's the formula for entropy. So when I is equals to 0, the Pi is 0.5. So that's negative 0.5 log to base 2 of 0.5. Minus, when I is equals to 1, Pi is 0.25. So 0.25 times log to base 2 of 0.25. Then minus, when I is equals to 3 and 4, they are the same. So I can just do minus 2 times 0.125 log to base 2 of 0.125. Then if you work it out, you're going to get an answer of 1.75 bits per symbol. Bits per symbol. So that's just a direct substitution that should be quite easy to get the entropy of that function. So what this means is, if I write my information source, I could say S0, I map it to 0, then S1, I map it to 1, 0. So I'm mapping them to binary sequences or binary, so coding. Then S2, I can map it to 1, 1, 1. Then S3, I can map it to 1, 1, 0. Now we'll look at this later, but this is what we are calling encoding. We are going to look at it later in the session, encoding. So you can actually calculate the average bit, because this is a very efficient code. If you want to compress data, that data that we've been given, you can use these codes to compress it. And that's an efficient code, which you can actually see that the average actually if you try to get the average here, average bits per symbol, so the average here, we know the probability of this one is 0.5, the probability of the other one is 0.25, then these two, 0.125, 0.125. So the average is always given by, the expected length is always given by pi times li. So that's how you get the average, but we're going to talk about this in a few minutes. So you can calculate the average. This is the length of that code for that specific symbol, S0. So for S0, our length is 1, our probability is 0.5. Then for S1, our length is 2, our probability is 0.25. Then for S2 and S3, the length of the symbols are both 3 times 0.125. And then there are 2 of them. So we can add 2. If you work it out, actually, you get this as 1.75, which is actually equal to the entropy. So we can see, and we're going to talk about this in a few, and why this is a scenario, but you can see that we are getting a value that is similar to entropy when we encode this thing optimally. So one of our goals in this lecture or in this course is to determine how do we actually achieve these optimal codes for compressing this data. Now, let's say something. So let's say each symbol S are equiprobable. So let's add that condition. So Roman 2, but then the solution of this question ended here. So let's say each symbol in S are equiprobable. That means they have the same probability, they're equiprobable. What does that mean? i.e. PO, probability of symbol 0 is equals to probability of symbol 1 is equals to probability of symbol 2 is equals to probability of symbol 3, and all these will be equiprobable, so we just give them a quarter as their probability. Now, calculate the entropy again. And let's see the difference. Now let's calculate the entropy again when these symbols are equiprobable. So all of them have the same probability, 1/4. So the entropy of this symbol now becomes h of s, and h of s we have I from 1 to 0 to 3, pi is what? 1/4 log to base 2 of 1/1/4. Okay? So those are the symbols that you're going to have, and that's really going to just give me, because they're all the same, so I can just put these 4 outside and then have inside 1/4 log to base 2. 1 divided by 1/4 is just 1 times 4, which is 4, and 4 is just 2 to the power 2. So log to base 2 to the power 2, this is just 2 log to base 2 of 2, which is 1. So this is 4 and 4, this becomes 2 log to base 2 of 2, and this we know is equals to 1. So our answer is just 2 bits. 2 bits per symbol. So you are seeing that when they are equiprobable, and we are getting a higher entropy when they have all this, when they all have the same probability, we are getting the higher entropy. So now we can write a conjecture that follows that slide. So you can say entropy is actually maximized when all the symbols in the alphabet are equiprobable. Okay, so that's a good conjecture to write, and you can actually show the proof. entropy is maximized when all the symbols in the alphabet are equiprobable. And then I will not show you the proof on the board, but is this important? Actually it is. Have you done anywhere Jensen's inequality? Okay. Let me do this and then bring it in the cart so that let's do this proof. Now, let's start with this proof, entropy maximization. I'm doing this proof not because I want to show you how to maximize entropy. Entropy is only going to be maximum always when we have a uniform distribution. So if I have m alphabets, if I have m number of symbols in an alphabet, then the maximum entropy is just going to be log to base 2 of m. So that's the upper bound. We cannot be able to exceed that. Then of course we know entropy cannot go below 0, it cannot be negative, so that's always a bound. But now we want to show this, but I'm using it to kind of teach you or introduce you to Jensen's inequality, which is a very important inequality in communication. So let's start with the concave function, okay? So if you start with the concave function, what you're going to have here is going to have such a function. Actually, let me just. So I'm going to have this function, and that's a function f of x, okay? Then I'm going to get 3 points. So I have a point here, x1. So at this point here, this function is f of x1. Then another point here, x2. And this is a function f of x2. Then I can get a midpoint. Then this is here and here. So now we're going to analyze this function a little bit. So I want to pick another point here and pick a point such that this is going to be theta x1 plus 1 minus theta x2. And then my theta is just between 0 and 1. Both of them inclusive. My theta is between 0 and 1. So let's work on that function. So if I look at this function, actually, the value here is just going to be f of theta x1 plus 1 minus theta x2. Okay? But now we have a straight line here. We have a straight line here. So the value of this point here is just going to be theta times f of x1 and then plus 1 minus theta times f of x 2, okay? On the straight line, because if you look at the equation of this straight line, then you can be able to show that actually this point is going to be that theta. Now, here we write, for a concave function, if you have any x1, and theta between 0 and 1, for any x1 and theta between 0 and 1, such that this function, f of theta x1 plus 1 minus theta x2 is less than or equal to, sorry, is greater than or equal to, because it's above this one, is greater than or equal to theta of f of x1 plus 1 minus theta of f of x2. That's not good. x2. This function, if a function exists such that this is true, then that function is what? Okay, I'll get that there. That function is called a convex function. That function is called a concave, sorry. So a good one is a logarithm function. Logarithm functions are concave functions. So they must satisfy this condition. So that means the function will always be above a chord. So we have this chord here, and then the function will always be above a chord. So that's a chord. And those are concave functions. A good example of this one is f of x is equals to log to base 2 of x, the logarithmic function. When x is 0, this log is always going to be, infinity. Then when x is 1, the log is going to be 0. And then finally, when, so this is x, and then the function, this is 1. So that's how the logarithmic function looks like. So, okay, this function is the function of log to base 2 of x. That's an example of a concave function. So log to base 2 of x is concave because if you, this is just one smooth function. Because if you draw a chord, the curve is always above the chord, and those are concave functions. So, but you can also do this using your calculus 1, the second derivative test, to test whether this is actually a concave function or not. So what you do, you just obtain the second derivative test. So when you differentiate twice, the second derivative is always less than 0, which means that function is concave, okay? So you can use second derivative test. I think you did that in calculus 1 on when you're doing optimization. So you can show that with the second derivative test, which means I can write my function. So if I differentiate f1 of x, what's the derivative of f1 of x? Of f of x, log 2 to base x, what's the derivative? What's the derivative of a log? But that's a natural log, yeah? So what about log to base 2? Okay. So it will be 1 over ln2 times 1 over x. Okay? 1 over ln2 times 1 over x. Then you can differentiate this again. The second derivative is just going to be what? 1 over ln 2 times minus 1 over x squared. minus 1 over x squared. Okay? And this value, f, the second derivative of 2 is always less than 0, which implies that f of x is equals to log 2 base x is concave. So that's called the second derivative test. So the concave functions will always satisfy that condition. Now let's try to replace theta with probabilities, because probabilities are also between 0 and 1. Probabilities are also between 0 and 1. So let's try to replace thetas with probabilities, which means we can now have, so if I have my theta be equals to P1, and then 1 minus theta be equals to P2, so that this one implies P1 plus P2 is just equals to 1. So P1 and P2 are probabilities, yeah? P1 and P2 are probabilities. So what you're going to see here is our function now can look like f of P1 x1 plus P2 x2 is greater than P1 f of x1 plus P2 f of x2. Okay? That's a scenario where we can say. Now, this is still a concave function. That's still a concave function. Now, if you have more than two p's, so if you extend it to more than two p's, extending to more than two p's to P1, P2 up to Pm. So if you have m alphabets, then this function is going to look like this. So we add all of them. As long as P1, P2 plus up to Pm is equals to 1, we can write this function as f, then we can sum inside. You see here we are summing inside, so I is equals to 1 up to m of Pi xi. Okay? And then this should be greater than or equal to, then our summation now is outside. So I from 1 to m Pi f of xi. So that's the new version of or the extension. So if you have more than two p's or more than two probabilities, that is your function. That is your function. I will put this one in a box. So this function here generalizes the definition of concavity for m points. This one generalizes the definition for concavity for m points. This function here. It generalizes the definition for concavity for m points x0, x1, x2 up to xm. Now I want you to take notes and see something. That there's this function here, I is equals to 1 to m, Pi of xi. What is this function? Anyone? What is that function? What do we call that function? Yes. Maybe for 1 second, stop being secretaries and think a little bit. What is that? It does no, because xi is, we don't know what xi is. But yeah, similar to what. But what were we calculating when we were calculating the length? Because I know you've just gone back to your notes and checked. What is this? This is the expectation of the average. Please guys, I encourage you again to go and read probability. Make it stick on your fingertips. Because you'll be looking, especially at that cut next week, and you'll wonder what's happening here. You have to know probability in and out. So this is actually the expectation of the random variable x. So for a discrete random variable, we always write the expectation like that. Okay? And then if you have another function, the second function now, I from 1 to m, p of I, f of xi. Now what is this? This is now going to be the expectation of the mean of f of x. Okay? So those two things. Now, if we look at that, we can nicely show that actually we can write this thing as in terms of expectations. We can write it in terms of expectations. So we can say that the function of expectation of x, because that's this part, is actually greater than the expectation of the function of x. And this is probably one of the most important inequalities in your life as a communications engineer, or as just even a scientist. This one here, we call it Jensen's inequality. We call these ones Jensen's inequality for a concave function. For a concave function. So I'll give you a 3 marks questions and tell you to prove the Jensen's inequality for a concave function. Now, if it was a convex function, you just change the direction of the inequality. You just change the direction of the inequality. So, inequality is reversed for a convex function. Okay, now, how do you prove maximum entropy? You prove entropy maximization using this Jensen's inequality. So we were not studying Jensen's inequality. That one you should have done in probability. Now the role of this Jensen inequality for us here is to prove maximum entropy. And how do you prove maximum entropy? So remember, we said, are we here? My favorite secretaries. You just write. Do you ever read these things? Because every time I ask a question, it's like you've forgotten again. Yeah? You just write. Yeah?
Probability is my weak point.
It cannot be a weak point. The whole unit is probability. Everything.
I know as you go, but I tell you.
No, you cannot know as you have to go through probability now before we go, because even the next lecture is just probability. So go and read it. You know, I used to think probability was actually hard. Then I dedicated time to reading it and doing a lot of practice questions, and it became quite easy. Very easy, actually. So we finish this proof, and then we can take a short break and come back. So we say that entropy Hs is equals to summation from I is equals to 1 to m of Pi log 1 over Pi. That's log to base 2. Yeah? That was our entropy. Now that is, if you look at this function properly, which side of this inequality is that function representing? We've already written this equation before. That function is expectation of the log. And the log here is a concave function. So it's this side, okay? It's expectation of pi, summation of pi log of this. This is just the expectation of this function, fx. Fx here is our log 1 over pi. So if you don't want to forget, your f of x is just log 1 over pi. So this means we can actually write this thing as less than or equal to, so we are applying this inequality, function of the expectation. So that means I can take now it to be function, which is log 2 base 2 is our function. Then the expectation in this case now is going to be what? I is equals to 1 to m pi times 1 over pi. Okay? So this bound is important. Then if you look at this one is just going to be equals to, this side is going to be log 2 base 2, pi times pi is 1, yeah? So summation from I is equals to 1 up to I is equals to n of 1 is just, okay, let me just write it, I is equals to 1 up to n of 1, okay? That just becomes what? Log 2 base 2 of m, log 2 base 2 of m. So here, oh sorry, and this is h of x. So here, we can actually see that h of x is less than, we are putting this inequality, log 2 base 2 of m. And that's the proof for entropy maximization. That is maximum entropy for a discrete random variable. So the maximum entropy is obtained when all the probabilities are equiprobable. Or all symbols are equiprobable. Okay? So the maximum entropy occurs when all symbols are equiprobable. Now here, by then, don't forget, your m is just what? The number of symbols in the alphabet. Number of symbols in the alphabet. So for Bernoulli sauce, how many symbols do we have in the alphabet? 1, 2, 20 probability.
27.
Bernoulli sauce.
Oh, I mean, in the alphabet. Using.
Wait. All this time you're talking about alphabet, you think it's the alphabetical letters.
I thought you were just asking a random question, like how many letters
And they are not even 27. Where did 27 come from? So how many symbols are in the alphabet of a Bernoulli sauce? Do you know Bernoulli sauce? Bernoulli sauce, Frederick? Bernoulli annuator. Is that correct? Bernoulli sauce. How many symbols? Well, itabidi nimwakishe tu mapema. Yeah, your probability to amaliza. Go and read it. Like, what do you do, guys? You don't read? Or you just expect to miraculously understand? Yeah, I will not tell you that. I've mentioned it like even 2 times already in this own lecture. You've probably just not listened enough. That's why I always prefer you listen first, then become a secretary. You listen, then become a... Because when you keep writing, you keep not listening. So just write, summarize these things. So entropy is maximized. That's just a repetition anyway. When all the symbols are equiprobable, i.e. P of 1 is equals to P of 2 is equals to R2, P of M, if we have M symbols, and all of them are 1 over M. This is a uniform distribution. This is a uniform distribution. My encouragement or my advice is not encouragement, it's advice. Go and take like 4 hours, just sit down and read probability back to back and do examples. Because probability is not tested in the CAT, it's applied in the CAT. So we assume you know probability. I only reviewed it because the syllabus requires me to review it, and they know it was taught earlier on, probability and statistics.